So let's now talk about a spring. What I just did with the pendulum, I can do something similar with a spring. Similar in the sense that at time t equals 0, I stretch the spring a little and I give it a kick, and then I let it oscillate. Very similar to what I just did, but now it is a simpler problem because the spring is exactly one-dimensional. Let this be the relaxed length L of the spring. This is point A. I stretch it to point B. I give it a kick. I will not put in any numbers now. I'll give it a speed VB, and it comes to a halt here at point C. Let the spring constant be K, and we know we're going to get a, so this is at t equals 0, we're going to get a simple harmonic oscillation, x equals x max. This is going to be x max. This is going to be xb, and this is x of a, which is 0. So we're going to get x max times the cosine of omega t plus phi. The same old story. It's getting pretty boring. Omega equals the square root of k over m, and t equals 2 pi divided by omega. These equations you will not see on your exam. What is now x max? How would you approach it? You've just seen how I did it with the pendulum. I used first the conservation of mechanical energy. There was no friction. And then I showed you that it's completely consistent with the work energy theorem. So what would you do now? How do we get x max? Any suggestions? Any proposal? Come on. You must have learned something from the last 10 minutes. Any idea? It's the same concept. We know the initial conditions, and we know it's a simple harmonic oscillation, and we want to know what the maximum displacement is going to be. Anyone? The courage to speak out. In the worst case, you're wrong. Believe me, I am wrong so often, if only you knew. So speak up. Shall we try the conservation of mechanical energy? Is anything wrong with that? Maggie, nothing wrong with it. Let's try the conservation of mechanical energy. The conservation of mechanical energy tells me that the kinetic energy at A plus the potential energy at A must be the kinetic energy at B plus the potential energy at B, and that must be equal the kinetic energy at C plus the potential energy at C. Right? There's no friction, there are no non-conservative forces, so this got to work. Well, the potential energy at A is 0, because remember, the potential energy of a spring is 1/2 kx squared, if x is the displacement from its relaxed position. So this is 0. When it comes to a halt here, this is 0. When I watched this lecture, I noticed a slip of the tongue. Clearly, the potential energy at A is 0. That's fine. But at C, the object is standing still. So at C, it is the kinetic energy that is 0, and not the potential energy. And I continued the problem correctly, because I wrote down here 1/2 k x max squared, which is exactly this term. That is the potential energy at C, which reaches a maximum. It is the kinetic energy that is 0 here. And I accidentally mentioned that it was the potential energy that is 0, which is obviously not so. So we get that 1/2 m VA squared equals 1/2 m VB squared minus 1/2 k x of B squared. That is the potential energy at this location. And that equals 1/2 k x of C, which we have called x max squared. And you are in business. If I tell you where the object is, with the pendulum I gave you the initial angle, my theta 0, I tell you where the object is, so you know x of B. I tell you what speed I gave it, so you know this one. You can calculate what the maximum displacement is. Exactly the same idea. And if you want to apply the work-energy theorem, of course, you will get exactly the same result. This is, in fact, the same thing.